So in this lecture we are going to discuss some properties of elements integral over a ring. So again, recall the definition of elements integral over a ring. So we fix a ring R and say A is a subring of R. So then an element X of R is called integral over the subring A if it satisfies any of these conditions A, B, C below. So the first one is you take the coefficients in ring A, and then you have a polynomial like this. This is a monic polynomial, and X is a root of this monic polynomial with coefficients in A. So obviously that's why it is set equal to 0, because this is a monic polynomial. Once you plug in X, this will be 0. So then X is called integral over this ring A. Or you can say this ring AX is an A module of finite type. Or you can say there exists a subring B of R, and this B contains A, and this is like this. So B of R, it contains A and it also contains X. So B contains both A and X, and this B is an A module of finite type. Then also X is integral over A. So this condition is also useful. So let us now derive some results using this definition. So in the previous lecture we showed that all these three conditions are equivalent. So first let us state first proposition, proposition 1. So say R is a ring and A is a subring of R. So A sits inside R, and this x1, x2 all the way to xn. So this is xi, I going from 1 to n. So x1, x2 all the way to xn. There are some finite set of elements of R. So there are n elements of R which we have picked up and named them x1, x2 all the way to xn. Now if for all I, xi is integral over this. So we have seen here, if you just pick up x, then ax, so this x is integral over A. So you keep adjoining. First you adjoin x1, so it's like this, then you get a new ring ax1, then to it you adjoin x2, then to it you adjoin x3, and so on. So at I minus 1 stage you adjoin xi. So we are saying that every time you adjoin a new element, that becomes integral over the previous ring. So similarly here, inductive procedure. So you have x here, then x1, and so on. So in particular, if all the xi's are integral over A, so every time you each add xi which is integral over A, you keep adding it, then this ring ax1 to xn is an A module of finite type. So we will see the proof, and the proof is kind of tautological, but let us first see two important corollaries of this. So the first corollary is that say R is a ring, and again A is a subring of R. Same thing here, R is a ring, A is a subring of R, and say x and y are elements of R, and both x and y are integral over A. Then x plus y, x minus y, and xy are integral over A. So let us prove this. So let us start with this ring AXY. That's the only thing we can do. So we start with this ring AXY. So obviously x plus y, x minus y, and xy, they lie in this ring AXY. Now according to this proposition, since x and y, we are saying x and y, which are elements of R, are integral over A. So instead of ax1 to xn, we have axy. So this axy, because x and y are integral over A, this is an A module of finite type. So according to the proposition, axy is a module of finite type. Now in the part C, we can set this subring B as axy. So this subring B is say axy, it obviously will contain A, and this is also an A module of finite type, because that's what we are saying, axy is an A module of finite type from our proposition. So then according to this proposition, x plus y, x minus y, and xy are integral over A. So that you can see, you set B as axy, A is as such, so instead of x you can write x plus y. So by proposition C, this part C of the definition, we know that x is integral over A if there exists a subring B which is of a module of finite type. So now we are saying there exists a subring B which is AXY of R which contains A, and it contains X plus Y because it contains X plus Y, which is an A module of finite type. So X plus Y is integral over A. So in this definition, X was integral over A. In this in part C, now we have replaced X with X plus Y. So X plus Y is integral over A, and B we have replaced with AXY. Same case with X minus Y. Again you set B as AXY. So there exists a subring AXY of R which contains A. This AXY is an A module of finite type which is given by this proposition. Therefore this X is integral over A, but instead of X we are writing X minus Y. And again you can do the same procedure. Instead of X plus Y you can write X times Y. So this entire thing comes from this last line of the proposition and this part C. Now coming to corollary 2. So again say R is a ring and A is a subring of R, and say you have a set A prime of elements of R which are integral over A. So you have A prime which is elements of R which are integral over A. So A is a subring of R. So this A is contained within A prime which is contained within R. So that's what we are saying. So A prime set of elements of R which are integral over A. This is a subring of R and it contains A. So the corollary 1 implies that A prime is a subring of R because you have elements. A prime consists of elements which are integral over A. So you take those elements integral over A, so x1, x2 all the way to xn. So they will again form a subring. So A prime is a subring of R. So this follows from corollary 1. Just the statement here. So we have A is in A prime. This is kind of obvious because if you take A in A, then A is a root of the monic polynomial here. So A is the root of the monic polynomial, and you can see this elements of A are automatically integral within A, and therefore A prime. So that's pretty much it. So this has coefficients in A, as you can see. So again here you can see that A is contained within this ring AXY. If you keep adjoining elements, A would be contained within this, and this tells us the same thing more formally. So let us now prove proposition 1. So again we had R was a ring, A was a subring of R, and we took n elements of R, x1, x2, x3 all the way to xn, and all these xi are integral over the previous ring. So you start with adjoining x1 which was integral, adjoin x2, x3, or keep on adjoining elements. Then in the end you get this A x1 to xn is a module of finite type. So in particular, if all the xi's are integral over A and you keep adjoining them, then you will get this as an A module of finite type. So to prove this is an A module of finite type, we need a finite set of generators. And the easiest thing to do is induction, because case n equals to 1 is right here in the definition. So here n is equal to 1. So for n equals to 1, we have repeat of assertion B of the definition. And from n minus 1 to go to n is also easy because you just adjoin the next element to it. So say B is A x1 to xn minus 1. This is an A module of finite type, so it will have a finite set of generators. So therefore you can write B as, say it has P generators, j equals to 1 to P A B j. So every element of B can be written in terms of basis elements B1, B2, B3 all the way to BP. So for the case n equals to 1, you can adjoin say B xn and you get this. And B is a module of finite type. So you can write Bxn as k equals to 1 to q B ck, because B is a module of finite type, because right here you can say if A is a module of finite type, you can just adjoin one element to it. So this Bxn will be a module of finite type. You're just adjoining one thing to it, so it still remains a module of finite type. So it will have some generators. So say it has q generators, so you can write it like this: k equals to 1 to q b c k. So it is a module of finite type, precisely because you're adjoining an integral element to it, and it is a this is a b module of finite type again. So this bxn, you have to notice it is a b module of finite type. So therefore the coefficients here are in b. Notice that the coefficients here were in a and the coefficients here are in b, because bxn is a b module of finite type. So now you know this is nothing but bxn. That is the definition here. So bxn we are writing like this. Now instead of b, you can plug in this a b j, and that's what we do. Instead of b, we plug in a b j, and this entire thing you can write it as sum of j and k, and our generating set is bjck. So bjck, j is finite, goes from 1 to p, and k is finite, goes from 1 to q. So you get a finite set of generators for this ring as a module over a. So this has a finite set of generators as a module over a, so you have a module of finite type. So now we talk about transitivity. So say C is a ring. Now B is a subring of C. So C is a ring, B is a subring of C, and A is a subring of B, and A sits right here. Now B is integral over A, so B is integral over A. C is integral over B, C is integral over B. Then this proposition says that C is actually integral over A. So to prove this, we are going to crucially use this result again, that this ax1 to xn is a module of finite type. That is, you can keep adjoining integral elements to construct a bigger ring. So again, we will start with taking an element x and c and say x is integral over b. So x is integral over b. Let's use this a of definition. So you have some polynomial like this. So we have this polynomial xn plus bn minus 1 xn minus 1 all the way to b0, where each bi lies in b. Just like here each ai lies in a, here each bi lies in b, because it's integral over b. Now we construct a new ring b prime. So this new ring b prime, and this will contain a, because you will construct it like this. You adjoin these elements b0, b1 all the way to bn minus 1. That is all these coefficients, just like in this proposition. So you put all these elements together. So then x is integral over b prime also. Now b prime is a much smaller ring than b, because you're just adjoining only a few bi's to a to get b prime. So this is much smaller than b, but x is integral over b prime because it has a polynomial here, and all these coefficients are contained in this ring b prime. Now b is integral over a. So b is integral over a. So all these bi's, b1, b2, b3 all the way to b0 are integral over a. So therefore by this proposition, in this proposition all these xi's were integral. So in particular all the xi's are integral over a. So the proposition implies that b prime of x, which is a, b0, bn minus 1 all the way to x. So x is integral over b prime, so you're adjoining x to b prime, which is same as adjoining x to this thing. So this is an a module of finite type. So this is an a module of finite type, as you can see right here. So by definition C, you see that there exists a subring B of R which contains a and x, which is an a module of finite type. So finite type, this comes from here. This is an a module of finite type. So this is an a module of finite type, and this B here, we will set it as this entire thing. So because then this B will contain both our a as well as our element x. So here also B contains a and x, and this is an a module of finite type. So then x is integral over a. So by definition C, x is integral over a. So this gives us C is integral over A, because we started with x which was in C, so this x was integral over B, and then we were able to carry this x as integral over A. So now we will write a definition. So say R is a ring and A is a subring of R. So A is a subring of R. So the ring A prime of elements of R which are integral over A. So you construct a new ring A prime which is of elements of R which are integral over A. This is called the integral closure of A in R. So let A be an integral domain. So we have talked about integral closure of A in some ring R. So now we talk about integral closure of A within its field of fractions. So A is an integral domain and K be its field of fractions. So you have A is an integral domain, you constructed field of fractions. Okay, just like in integers we construct field of fractions Q. So then we can talk about integral closure of A in K. So now just like we talked about integral closure of A in R, we can talk about integral closure of A in K. Now that is called integral closure of A. So notice that this first one was called integral closure of A in R. This is called integral closure of A itself. So when it is just called integral closure of A, that means we are talking about integral closure of A in its field of fractions. So say B is a ring and A is a subring of B. So we say that B is integral over A. So B is integral over A if every element of B is integral over A. So that is if the integral closure of A in B is B itself. So you take an element B in B, then this B is integral over A, means that this B is going to be root of some polynomial like this. The coefficients are in A. So this is the easiest way to see. And when we are calling that B is integral over A, that means integral closure in B is just B itself. Notice that A is integral over itself because you always have a monic polynomial like this, where A lies in A. This A is within A. So A is always integral over itself. So we are talking about rings which are bigger than A. So now we talk about proposition 3, which says say B is an integral domain and say A is a subring of B such that B is integral over A. So then B is a field if and only if A is a field. So B would be a field if and only if A is a field. So we start with this, say A is a field and you take an element B in B so that B is non-zero. So our process is we are going to find another element B prime so that BB prime is equal to 1. So that will show that there is an inverse for every element B we choose. So first thing is that notice this B. So AX is a modular finite type. So we get AB is a finite dimensional vector space over A. So it just comes from B because B is an integral domain and B is integral over A. So therefore we can construct a map from AB to AB by just taking an element Y here and mapping it to BY. So this is a linear transformation of AB. Now it is injective because AB is an integral domain and this lies within this big thing B, because B itself is an integral domain given to us here, and B is non-zero as we have picked it right here. So this is injective, but this map goes from AB to AB, so it has to be surjective too. So it is surjective. So we have an inverse of 1 here somewhere, but this map is multiplication by B. So we have to have some element B prime here which we multiply by B to get 1. So there exists a B prime in AB such that BB prime is equal to 1, and that's precisely the inverse we wanted. So for any B non-zero B, B is invertible because you can find a B prime. So therefore B is a field. So conversely, suppose B is a field, and now we will show that A is a field. So this should imply A is a field. So we pick a non-zero element in A, and then A has a inverse in B, because B is a field and A is contained within B, where B is a field. So A inverse definitely lies in B. What we have to show is that this A inverse actually lies in A. So this A inverse is integral over A. So it satisfies some equation like this. So we put A inverse here, and this equation becomes this equation right here. So this is A inverse plus A n minus 1, this, and so on to AI in A. So now you multiply both sides by A n minus 1 and bring these terms to right hand side. So you know A minus n times A n minus 1 gives you A minus 1. All these terms to go to this side, you have negative signs coming in here. The A n minus 1 multiplied by this will just gives you 1. So you have A n minus 1, and this A0 you're multiplying with A n minus 1. So now this shows, now all these elements are in A, because here we say that all these elements lie in A. So all these elements are in A. So this A inverse is just a linear combination of these elements. This A is also in A. Each AI is in A. So A inverse also lies in A, and therefore A is a field.